Today we'll be talking about chemical equations, and this is a topic that most people are already familiar with. Chemical equations are simply the recipes for chemical reactions. They tell you how much of one thing you need and how much of something else you need to form a certain amount of your product. Okay, and recipes are really a great metaphor for this. It's really easy to think about these as recipes, and it takes away that confusion of seeing all of these symbols that you might not be familiar with. Maybe you're not familiar with what sodium hydroxide actually looks like, but when you just think about it like a recipe, and you think about a familiar recipe that you know, then it becomes pretty simple. So on those lines, let's look at one really easy recipe for, in this case, for a turkey sandwich. Okay, so if we were writing the recipe for a turkey sandwich like a chemical equation, what we would do is on the left-hand side we would put our ingredients, but instead of ingredients, we call these reactants. And then on the right-hand side, we put what we're making, and that is our product. We put products because sometimes there's more than one thing you're making. And so in the case of a turkey sandwich, just to be really simple, we put 2 bread, so in other words, 2 slices of bread, plus 1 cheese, plus, we'll say 3 turkey, so like 3 slices of turkey, plus 1 tomato, plus 1 lettuce, becomes, our product is 1 sandwich. So that's essentially taking a recipe and turning it into using it in the same format as we would use a chemical equation. And one thing that I would say is different here is just that instead of when you only have one of something, you don't write anything. And so if we were writing this truly like a chemical equation would be written, we would take out the ones. You would just say tomato, we just say lettuce, we just say sandwich. Okay, because the ones, similar to our formulas, the ones are assumed. All right, now a couple of symbols you'll want to be familiar with. This S in parentheses means solid. Okay, and when you write this, when you use this S, for example, if you have iron solid, you would write Fe and then an S in parentheses as a subscript. Now, G means gaseous or just gas. And another example here would be O2, and then in parentheses we'd put a G. L, of course, means liquid. And we could just use H2O, and then put a little L here in parentheses. And then AQ, not as common, maybe that you might not guess what this means right off. That means aqueous. And what that means is when something's aqueous, that just means it's dissolved in water. So for example, if you had NaCl, NaCl is table salt, of course, but if for your reaction it needs to be dissolved in water, then you would put in parentheses AQ. Okay, so aqueous just means dissolved in water. One other symbol down here is this little triangle. That, of course, is the symbol for delta, and that just means that heat has been given off, okay, in that reaction. So a good example of that was the hand warmer that we used in, I think, one of the first labs. And, of course, when you shake that, it's exposed to oxygen. So iron, which is what's inside of that hand warmer, mixed with oxygen, gives off heat. So if you were to write that equation out, you'd want to have this little triangle in it showing that heat is given off. All right, now the next step is when we see a reaction written out in words, how do we put that into an equation? So first of all, we're going to only do what we call a skeleton equation, okay, and that, don't be thrown off by that. All that means is that it's an equation that's not yet balanced. So it's kind of like in our example of the turkey sandwich, kind of like saying you make a turkey sandwich by putting bread with turkey, with tomatoes, with lettuce. But you're not saying how much of each of those things you have. Okay, so we're going to start with one of those skeleton equations and then work from there to where we're balancing the equations. So on this one, we take iron 3 sulfide. Now, if you're not sure what iron 3 sulfide is, this is a good time to come in and talk to me, okay? Because this goes back to the naming that we did over the last couple of weeks. And it's going to be important now to be able to use that naming in these practical situations, because some of these problems, in order to get started, you've got to have that naming down. So you might need to review some of that. So the iron 3 sulfide reacts with gaseous and actually this is solid, so we need to put in parentheses here a little s. So it reacts with gaseous hydrochloric acid. Again, naming. Okay, this goes back to that little sheet that has the naming workflow. So you'll want to look at that again. But hydrochloric acid is HCl, and we want to put in parentheses a G for gaseous. And then it forms. So when we see that word forms, that means that this reaction is happening and it's going to form whatever products we have. And so we put a little arrow where we see form. And then we have iron 3 chloride. And again, if this doesn't make sense, come talk to me on how to write iron 3 chloride. And next, it also produces gaseous hydrosulfuric acid. Hydrosulfuric acid is H2S, and that is gaseous. We put in parentheses a G. Now, I will note here that where it says iron 3 chloride here, I do know personally that that is a solid, okay, even though it doesn't actually say it in the problem. So I'm going to put an S there. But if it didn't say it, then don't put anything, okay, if you're not sure what that is. I just happen to know that one, so I'll put the solid in there. So that's an example of just how to take words and turn it into an equation. All right, now we've got to go backwards on this one, and this is also relatively simple. We just have to take iron solid. So just to put an equation into words, we say solid iron plus gaseous oxygen react to form iron 3 oxide. So in this case, we have taken an equation and just turned it into words. The only thing that I should probably put here is instead of a plus, I should probably say and. So solid iron and gaseous oxygen react to form iron 3 oxide. Now that we know how to just write the skeleton equation, and again, the skeleton equation is simply the recipe without the amounts, now we need to figure out how to balance equations so that we can figure out if we're going to produce 3 sandwiches, how much bread are we going to need, or how much turkey are we going to need. So we need to make sure that it's balanced on both sides so that we are using the correct amount of ingredients to form or to make the correct number of products. And so there's 4 simple rules, and they're actually, we probably don't even need 4 rules. It's actually, we pretty much just need 1 rule. And that 1 rule is going to be number 3 on this list. But we put some extra ones in there just to help everything get started. So first of all, we assemble the correct formula, and that's what I was just showing you, is how to assemble that correct formula. And we use the pluses and the arrow in order to form that correct formula. The second step is we count the number of atoms of each type appearing on both sides. And that's pretty straightforward. If we've got 3 hydrogens on the left, we need 3 hydrogens on the right. And that's what you're doing in number 3, is you're going to balance the elements one at a time by adding coefficients. Okay? Now, that's the big word here, is coefficients. That's what you're going to be changing to make sure that the equation is balanced. Okay? You do not use the subscripts. You don't change those numbers. Okay? You only use coefficients. And if you're forgetting what coefficients are, I'm sure you remember that from math. It's the same thing as in math. But I'll show you what those are just to make sure you're clear on that on 2 slides away here. So, and then one other hint they give is they say that save the hydrogen and oxygen until last. And you'll find that is useful because a lot of times hydrogen and oxygen show up in more than one substance. And so by balancing one substance, you might mess up the other substance and kind of have to go back and forth. And then once you're done, always just double check to make sure everything's balanced. And what you'll find is even if you go about these in the wrong way, a lot of times you're still going to get to the right answer as long as you do that double check to make sure that ultimately what's on the left is exactly the same as what's on the right. Okay, there's a couple of cautions when it comes to balancing. So number 1 is never change a subscript. Okay, so in other words, in our example like H2O, so let's say the left side had 4 hydrogens and the right side has H2O. So we might be tempted to think, oh, I can just change this to H4O to have 4 oxygens on the right-hand side. Okay, that would be wrong because once we change it to H4O, we have a totally new substance. In fact, a substance that I've never heard of. Okay, So we can't do that. One thing we could do, though, is we could change the coefficient and put a 2 in front of H2O. That would be fine to do. Next, never put a coefficient in the middle of a formula. They must go only in front. So the example they give here is if we had on the right-hand side, if we had NaCl, but on the left-hand side we had 2 chlorines, we might be tempted to say Na2Cl, but that would not be correct. If we're going to have 2, we've got to have 2 of the whole substance. We can't have just 2 of one of the atoms, because that again would change our entire compound, and really Na2Cl is something that doesn't even exist. So it has to be, we have to make sure that we only change the coefficients. All right, now on to some examples. Let's just go through and we're going to balance these, and we're going to follow these rules and then put them into use in a practical setting. So first of all I do is I just choose one of the atoms on the left-hand side and then count how many there are and compare it to the right-hand side. And then if they're not the same, then I try to change a coefficient on either the left or the right to make it so that they're the same number. Then I go to the next atom, do the same thing. Then I go back and check to make sure everything's still balanced, because you'll see, in fact, in this equation, what you'll see is that when we change one of the atoms, it makes it so that our sodium becomes unbalanced, even though it was balanced originally. So we have to make one other change before we're done. All right, so let's go for it. First of all, we've got 1 sodium on the left and 1 sodium on the right. All right, so we're good there. Okay, next, now we always leave the hydrogens and oxygens until last, but we're at that point now. So we look first at the hydrogens. We have 2 hydrogens on the left, and on the right we have 2, and we've got 3 on the right and 2 on the left. All right, so that's kind of a tricky situation, okay, because we can't put 1.5 here, okay. That would be because we can't have halves when it comes to our coefficients. They have to be whole numbers. That's just by convention. So let me show you what I would do in this case. Let's try this. And again, if you just experiment and then go back and check it, it'll be fine. I'm going to put a 2 right here. Okay, so I'm going to make it so that there are 4 hydrogens on the right side, because we've got 2 right here, and then we've got 2 of this substance of sodium hydroxide, which has 1 hydrogen in it. So if we've got 2 of those, we've got 2 hydrogens there. So 2 plus 2 is 4. Okay, so now we've got 4 hydrogens on the right. We need to balance it out. We need to go back to the left, and we need to make it 2 right here as well. So now we've got 4 hydrogens on the left and 4 hydrogens on the right. So now for hydrogen, at least, we are balanced. Now let's go to oxygen. Oxygen now has 2 oxygens on the left, and it's also got 2 oxygens on the right. So we are balanced with oxygen now that we've made this change that we just made a moment ago. But the last step is we always go back and check to see if everything is balanced. So let's go back to our sodium again. So sodium, we have 1 on the left, and now we have, we've got 2 on the right. Okay, so now we have something that is not balanced, even though it was balanced before. So now we need to add a 2 right here on sodium so that it's balanced on the left and the right. Now let's go through and check everything else. We've got 4 total hydrogens on the left, and we have 2 plus 2 is 4 total on the right. And then oxygen, we've got 2 on the left plus 2 on the right. So this equation now is balanced. We're good to go. Now this next one is, we've got sodium nitrate plus copper. It becomes copper 2 nitrate plus silver. So let's go ahead and see if this is balanced. Let's look at the silvers first. We've got 1 silver here on the left, 1 silver on the right. So we're already balanced there. That's not too difficult. Now let's go on to nitrogen. Nitrogen, we've got 1 nitrogen on the left, but look on the right, okay, because we've got 2 of our polyatomic ion, nitrate, and we've only got 1 on the left. So now with nitrogen, we've got 2 on the right, 1 on the left, so therefore we need to put a coefficient of 2 right here to give us 2 nitrogens. Okay, now let's look at oxygen now. So we've got O3 times by 2, so that makes 6 oxygens on the left, and we've got NO3, and we've got 2 of those NO3s, so that makes 6 oxygens on the right. So our oxygens right now are balanced. And then finally, copper, we've got 1 copper on the left and 1 copper on the right. Now again, the last step after we've checked to see if everything is balanced, or after we've gone through each and balanced them, now we need to go back and check to see if everything is still balanced. Let's check our silver first. We've got 2 silvers on the left. We've only got 1 on the right. Okay, so we need to change that. Let's put 2 right there. Let's go back and check everything else. 2 nitrogens, 2 nitrogens, 6 oxygens, 6 oxygens, 1 copper, 1 copper. Okay, we have a balanced equation now. All right, now finally, this is the equation for when you take methane, natural gas, and you burn it, okay, or you explode it in some cases. So we've got methane, CH4, plus oxygen becomes CO2 plus H2O. Let's start with the carbons. Carbon, we've got 1 carbon on the left, 1 carbon on the right. Good, we're good to go there. So we want to leave the hydrogens and oxygens for last, which we're at that point now. So let's look at hydrogen. We've got 4 on the left, but on the right we've only got 2. So in order to balance that out, we're going to need 2 waters. Okay, that'll give us 4 hydrogens on the right and 4 hydrogens on the left. And then we go to now oxygen. We've got 2 oxygens on the left, but on the right we've got 2, 4. All right, so oxygen, we're going to need more. Okay, so we need 2 more here, or 2 total of that O2. So that'll make 4 on the left and 4 on the right. So let's go back and check one more time to make sure we haven't thrown off our balance at all. We've got 1 carbon on the left, 1 carbon on the right. We've got 4 hydrogens on the left. We've got 4 hydrogens on the right. We've got 4 oxygens on the left, and then we've got 2 plus 2 is 4 on the right. That's a balanced equation. All right, well, that concludes our video on balancing equations. And you'll see, just like as we worked on these, you'll see that you just jump into it and you go and you try different ways of balancing the equations, and eventually you'll get there. If you just follow that simple pattern of comparing what you've got on the left to what you've got on the right and only changing the coefficients. Let me know if you have any questions, and we can go over those in class, and I'll talk to you next time.